Welcome to this video. Thanks for watching. I'm going to begin solving this practice exam for AP Precalculus. This is given by the College Board, actually. So this was written by the College Board, and it's actually given to instructors as practice or as a resource. You actually, if you're not even an instructor, you can Google search for this really easily. That's how I found it. Okay, so I know the AP Pre-Calc exam is coming in like 2 months. So people are going to start studying. So hopefully this can be helpful for you if you're in that studying phase. Okay, so I'm starting with number 1. This is the no calculus section. A polynomial function p is given by this guy. What are all intervals on which p of x is greater than or equal to 0? Okay, so we are going to do the sign test here. So in calculus, we're going to find the critical points. I don't know if that sounds familiar for you, but we want to find where p of x is equal to 0. Okay? At what values of x? Okay? So if this guy is 0, that could be when negative x is 0. I taught this the other day to a Math 2 student. This is the zero product property, they call it. But not to get technical into how you name stuff, but we're going to set p of x equal to 0. How do we do that? Negative x could be 0, x minus 4 can be 0, or x plus 2 can be 0. Okay, so we know that, so I called the critical points, our x is 0, 4, and minus 2. These would make our p of x 0. Okay, so I know some teachers make you do it the long way, where you have to write all the intervals out from like negative infinity to negative 2, from negative 2 to 0, and 0 to 4, and then 4 to infinity. You have to write all these out. And then you would kind of make the sign charts from here. Okay, it's totally fine, so let me just do it like this. We're going to plug in some number between negative infinity and negative 2. Okay, so most teachers tell you to actually plug in the number in. For example, we can plug in negative 3 into here. And then you solve it out and you find out what the final number is and you figure out if it's positive or negative. Okay? I don't recommend you to do that, actually. Instead, we only care about the sign. So let's plug in a huge negative number, like negative 1,000, something like that, negative 1,000,000, even more negative. We only care about the sign. So when we plug in a big negative number into negative x, like negative 1,000,000, it would become positive. When we plug it in here, it'll be negative here. And then over here, when we plug it in, it'll still be negative, like negative 1,000,000 plus 2 is still negative. So we have a positive and 2 negatives, so this total sign at the end would be positive, because 2 negatives make the positive. We plug in some number between negative 2 and 0, like negative 1. Again, you don't need to actually find the value, we only care about the sign, so this is what I'm trying to show you. When we plug in negative 1, this would become, the negative x would make it positive. When we plug in negative 1 here, it would be negative. Plug in negative 1 here, it would be positive. Okay, so we have 1 negative, 2 positives. So the sign is negative. You plug in a number between 0 and 4, for example, 1. This is negative, this is positive. 2 negatives make a positive. Plug in some huge positive number, this would be negative, this would be positive, this would be positive, so the sign is negative. So we're interested in when p of x is greater than or equal to 0. Okay, so that's when it's positive. So from negative infinity to negative 2, and from 0 to 4. So that is D. And that's the answer. So I do have the key and I'm checking it as I'm solving this live. Okay, so you can do it like this. The way I teach people, at least in calculus, is to do it like this. It's the exact same thing. We're going to use our critical points and draw it on a number line. And then instead of writing all this out, because this is a time test, this is going to take more time, especially in multiple choice where you don't need to show your work, just do something like this. And then you have your intervals exactly, same as here, from negative infinity to negative 2, between negative 2 and 0, 0 and 4, 4 to infinity. And then you plug in numbers again. So I would write it like this. Something like that, as I'm figuring out, so that I know that these two are the positive regions. And that will be my answer. So I usually solve it like this, but this is the way that teachers usually tell you to do it, the sign chart type of thing. All right, let's move on. Function f is given by 9 times 25 5 to the x power, which of the following is an equivalent form for f of x. Okay, so how can we solve this? Well, just by looking at the choices and looking at the numbers here, we know that it has to be related to like 3 squared and 5 squared somehow. And then we have to simplify it into one of these forms, okay? So let's just directly work from here. So f of x would be equal to 3 squared times 5 squared to the x power, okay? Which we can write as 3 squared. This we can write as 5 to the 2x power. Properties of exponents. When we have this guy to something with an exponent to another exponent, we multiply the exponents like this, okay? And actually we can't do anything else. So it would be 9 times 5 to the 2x. So the choice is D. The correct answer is D. Okay, so this is just a simple property of exponents. The figure shows the graph of a function f. The 0 and extrema for f are labeled. The 0 and extrema, this is not an extrema, but okay, whatever. And the point of inflection on the graph of f is labeled. Let a, b, c, d, and e represent the x-coordinates at those points. Of the following, on which interval is f increasing and the graph of f concave down? Okay, so we can easily find out when f is increasing. That's from a to b, and then from b to d is decreasing, and then d to e is increasing again. So it's either a to b or d to e, one of those. That's when f is increasing. So we took care of the easy part. How about f is concave down? Over here, it opens downward, so it's concave down. Over here, it opens upward, like the bowl, it opens upward. Like over here, the bowl is upside down, so it's concave down. The bowl is right side up if we think of the bowl like this. So that's concave up. So we are interested when it's concave down. So that is from A to B. Easy. Function f is given by this guy, which the following describes the end behavior of f. So end behavior, that's the limit when f when x approaches negative infinity and when x approaches positive infinity, okay? So when we have a simple polynomial like this, you can imagine as x approaches infinity, so x gets bigger and bigger, like x approaches like 1 million, 1 billion, 2 billion, so on and so forth. When you have like 2 billion to the 6th power, that's much bigger than 2 million to the 3rd power ever could be. So as x gets bigger and bigger, this term will be the most significant one. These two are very insignificant compared to this x to the 6th term. Okay, so we only care about this. Now, as x approaches infinity, so as x gets bigger and bigger, this term is always positive, so it's going to be positive infinity. So we can eliminate a and d already, because as x approaches infinity, it should be positive infinity. Now, as x approaches negative infinity, so x is getting smaller and smaller and smaller, once again, these two terms are insignificant, so we only care about this. When x gets more and more negative, well, the negative number is always to the 6th power, it's the even power, so it's always going to be positive. So it's going to approach positive infinity. Answer is B. Okay. If you go on to take calculus, this is simple limits. Let's move on. Let x and y be positive constants, which the following is equivalent to 2 ln x minus 3 ln y. So we're going to use properties of logs. I already can guess what we're going to do. We're going to move this coefficient out in front back as an exponent inside the log. So it'll be log, so instead of natural log, I'm just going to say log. That's what a lot of people do actually. Log of x squared minus log of y cubed, like this, is equal to that. Okay, and we can use the property where when we have a difference of two logs, it's the same thing as the quotient of the argument. So x squared over y cubed. And 5 looks like is a then, as simple as that. Properties of logs here. Polynomial function is given by p of x as this guy, which the following describes the zeros of p. Okay, so can we factor this guy? it looks like we could, because p of x would be, so the x plus 3 remains the same. When we factor this over here, it would be x and x here. There should be a plus and a minus. It should be 5 and 3, so it would be negative 5 and plus 3 to get minus 2. Okay, so we factor it like this. Okay, so notice there's a repeated 0, so that's probably what they're trying to test you for. Okay, so let's see what the choices say. P has exactly 2 distinct real zeros. P has exactly 3 distinct real zeros. We already know that's not true because there's 2 distinct, and of those 2 distinct, one is repeating. Actually, what do they call as distinct? Let's keep reading because I'm not sure, because I'm not a teacher of AP Precalculus. I'm just a tutor. So let's see what the other choices say. P has exactly 1 distinct real zero and 2 non-real zeros. There's clearly real zeros here. And actually, let me read that again. P has exactly 1 distinct real zero and no non-real zeros. And then D is P has exactly 1 distinct real zero and 2 non-real zeros. So we can already eliminate D because they're all real zeros. Okay? Does it have 1 distinct real zero? Well, there's 2 distinct, like unique. Distinct, unique, same thing. So not C. 3 distinct real zeros? No, that's not true, so it should be A. Yep, and that's the answer. So 2 distinct because there's 2 unique. This is a repeating one. In the xy plane, the graph of a rational function f has a vertical asymptote at x is -5, which the following could be an expression for f of x. So we need a vertical asymptote at x is -5. So let's go choice by choice. Over here, the vertical asymptote is at x is equal to +5. So it's not that. Over here, there's a hole at x is -5, or a removable discontinuity. I'm not sure how you call it in AP Precalc. Maybe I think you call it a hole, not a removable discontinuity. That's more of a calculus term when we talk about continuity there. But anyway, so this is a hole there. So it's not asymptote. Cross that out. Over here, once again, the asymptote is at +5. Over here, it looks correct. The asymptote is at x is -5 here. Okay. Let f be a sinusoidal function. The graph y is f of x is given the xy plane. What is the period of f? So the period is when it repeats itself again. So if we take this peak and we just count how many units it took until it repeats itself again. So it'll be 1, 2, 3, 4. So the period is 4. As simple as that. Okay, and actually call it apart here. Hopefully I went through slowly, so it's slow enough that you got most of the problems, especially like this one. I went quite slowly. Okay, please like this video if you found it helpful. Hopefully, if you got stuck on a problem, hopefully I was able to clarify it as I was solving it, and hopefully you were able to follow along. If you don't have a hold of this exam, hopefully you were able to pause the video and solve the problem before you saw my solutions. But anyway, please like this video once again if you found it helpful, and please subscribe also. And you'll also get notified for when I release the next part, when I solve the next few problems. So hopefully I see you in that video also. Bye.